Okay, so now we will see a second solution, which is the new big step semantics that uses more tools, but simpler tools, so it gets a bit closer to reality. It relies on renaming and creation of new variable names. I'll explain that below, don't worry. So now I first have a new bind function that takes the same arguments, but returns something a bit different. It still returns me a statement to be evaluated, a new store, but also an expression E that corresponds to what is inside the return, but a bit changed. So that's why I need to have it here. Then normally I evaluate the statement as prime that was returned from that, and in a new store sigma prime, and gives me a store sigma second. And I'll evaluate the return statement, which it's not exactly the return statement, it's something that looks like the return statement, and in the new store sigma second. And now I don't have anything to do with the store, I just have to update the store with the return value. So this really looks like what you would expect instead of the previous rule. I mean, it doesn't do any strange manipulation of variables because they are hidden in the bind function. But the good point is that we don't restore a store here. We just, in fact, what bind will do, and I will show you below how to do it, is that it guarantees you that in sigma prime, there's no clash of variables with the global or variables of the column. So sigma prime might be a bit too big, but at least, because it will contain new fresh variables, but at least you don't have to restore anything from this sigma after the sigma second. You just have some useless variables. How does this work? I mean, this all relies on the bind function. So I should now explain the bind function so that you understand more the details on the way it works. So my bind to function returns also a statement and a store and an expression E. Except that it doesn't map x to v1, but a z1 to v1. Zi are fresh variables. So basically it creates like if it was new variable names for parameters, so that to be sure that they don't clash with the variables that were inside sigma. Okay, so I create new variables and I bind them to the value that is given as before by evaluating the color, the expression in the color context. That's like before. Okay, so this is how I instantiate variables from x to zi. The problem is that now inside the statements of the body, x1 is used, but I should use z1 at the same place. So I have an operator that is called renaming or substitution that replaces inside SF all the occurrences of x1 by z1. Which basically, if you want an example here, if inside SF here, I add whatever y equals x1 plus 2, the effect of this renaming operator here is that it gives me same thing, but except of instead of z1 x1, I would have z1. So it replaces all occurrences of x1 by z1. I do this for all the variables, but I must also do this for all the local variables. All the variables that are inside df are local to the function, and they must not erase the other one. So I create a bunch of fresh variables ti. How many? Well, as many as I have local variables defined in df here. So for all of them, I create a fresh ti. And I also use this in the renaming of statements. Okay, so that gives me my new statement S prime F. So it's the same as SF, but with renaming corresponding to the fresh variables. And E is exactly the same thing. It's the return statement, the returned expression, but renamed the same way. Okay, so this is how I define everything. I didn't tell you explicitly how I find variables that are not used anywhere. So I use the keyword fresh that is very often used when writing semantics, but it just means that it's not used somewhere else. But generally, you want to give a real definition for that. And the formal definition of fresh in this context is that it's not in sigma and not among the other fresh variables. So you want to guarantee that all the fresh variables are distinct and that they don't belong to sigma, which is the sigma here. So you see it will be easier to modify this definition to have a formal semantics for fresh. Now I can come back to the rule so that you understand better what happens. So now I call this big bind function that just do a naming so that I have fresh variables, and I evaluate s prime in the environment in the store sigma prime, and in a big step it gives me sigma second. I can also evaluate the new return statement with renamed variables inside sigma second, and this gives me v. And now the evaluation of the function call is just to evaluate the body. It gives me a new store sigma second and associate x to v. So here it is. We had a couple of explanations on this rule, and we had an explanation on the binding. Everything is hidden in the bind function here, as you realized. So now what I suggest is that you also try to evaluate the following program. It's the same as before, but you will show that it's working a bit differently because of this renaming binder.
We start from the same initial state, so now you should know that it's the statement of the main, so just write S. M here, you know that statement of the main that just initializes x and y to 0, and then calls f of 3. And we place ourselves in an empty store here. And we want the big step that reaches the other. We do a sequence where we evaluate x 0 in the empty. It gives me x maps to 0. Another sequence remains here as the S2, which start by y 0 and then does f of 3. In the I put myself in the store sigma here, so this is sigma, and I should obtain something for evaluating the assignment of y to 0. It's a bit also something you know because we've seen it on the previous video, so I just do it fast. Now we get to the interesting part, which is the function call. So same thing now, I mean, as usual, you should have the rules at hand. Well, this was previously similar to before, so you might remember, but now we need to use a new rule. So the second solution for the big step semantics of the function call. So I first do bind of, so this is bind 2 of f3. It should provide me a s, I will keep the s prime here, sigma 2, and an expression e. Now let's have a look at the bind and see what those are. I unroll the bind in this corner here. So look at the explanation for the bind function. S prime is exactly the body. So the body, if you have a look at this example which is in front of me, x is assigned to 1 and y is assigned to 2, but with fresh variables, and fresh variables both for x because it's a parameter, and for y because it's a local variable. So this corresponds to zi and to ti in the explanation of the bind function. So I'll replace x by z, just to be coherent with the notations, and y by t. So in fact, S prime is S is replaced by z, so its z becomes 1 and t becomes 2. Similarly, I can compute E here. E is what is inside the return, so it's x plus 1, but renamed in the same way as the rest. So it's not x, it's z. So it's z plus 1. Okay? So now I have E, and I just miss the sigma 2. And if you can have a look at the bind rule, it says sigma 2 is sigma, which in my case becomes sigma 1, where I assign the parameters. So now I have z is mapped to 3. So it means it is x is mapped to 0, y is mapped to 0, and z is mapped to 3. So I don't know if you remember the other case, or you might want to have a look at your notes here. In the other case, the 3 was already had erased the x here. So here we see that somehow we remember the previous values of those variables, but we won't be able to access them because they have been hidden by the local variables. And it's important to notice that here. That's a tricky part. For the rest, it's quite standard. What you will do is that you will evaluate S prime sigma 2 by a big step semantics. It's a couple of assignments, so I won't do the rule for sequence and everything. It gives me a new store, which is the store that I had before, but where I applied the two assignment. So x is still 0, y is still 0, z is 2. No, z is 1. And t is 2. Okay, I have a new store, and I have another thing that I should evaluate is, I guess I can do it here. V equals the valuation of, it's not x plus 1, it's e, so it's z plus 1. In the new store, which is this one. This one I will call it, I have a sigma 2, so this would be sigma 3. So in sigma. Okay, so this gives me, of course, this is z plus 1, so it's 2. As before, not very surprising. The last thing I need to do is the new store. The new store should be sigma second if you look at the rule, which means the result here, so it is bit sigma 3, but now where x is mapped to v, which is 2. And so this gives me, I can compute it here, so this is sigma 4, and so this is sigma 4, 2, and sigma 4, what is it? It's x is mapped to 2, y is mapped to 0. That is what you had before in the previous case. But in our case, we also have z is mapped to 1 and t is mapped to 2. And you notice that this part here is not useful. I mean, it's a waste. This is useless. But it's fine, it's just a bit useless. But on the variables that are accessible, the true semantics agrees. That's something we could have proven during the course if you want. Okay, so same thing as usual. I hope you understand this explanation. Of course, I can, during the course, explain again or answer any questions or any requirement for further explanations.
Okay, now let's evaluate this second solution. The concerning variables, we remove the clash of variables, so it's much easier from a store manipulation perspective. Of course, it's still not really realistic in the sense that the store grows unbounded. We just add new fresh variables each time you do a fresh method invocation. However, we could detect the variables that are not used in the current statement and just remove them. So it would not be that difficult to get to something that is of a bounded size, but it would add one more operation somewhere that might be a bit tricky. Second problem is that variable substitution is not that easy to implement and not that efficient because you want to modify a whole statement that is roughly a whole method body, a whole function body. So it requires you to modify a big chunk of code. And if you had recursive blocks with function with other variables declared, then you would need other freshness of variables, and it can be you might have to do this a bit often, like each time you enter a recursive blocks. So it's still a bit far from reality because of this substitution of variable names. But you understand, I mean, it's still much closer than the previous solutions because we don't modify the store, which is supposed to modify the memory. We just modify the program. So it's clearly more realistic, but still something we can probably find something a bit closer to reality. So until now, we've seen two semantics for function call, and this is the third one. The two previous ones were already using quite classical tricks, or at least ways to write semantics for dealing with variables. And this is the third one, also a classical one, that gets us much closer to what can exist in the real system, and that is getting a bit more efficient from an implementation of the semantics perspective, if you want. So the idea is very simple. Instead of modifying the statements like in the previous solution by changing the names of the variables that exist in the statements, we now use an indirection. It's like if you were remembering the renaming or the substitution of variables we want to do, and we were applying each time we access a variable. This, in fact, if you think about it, corresponds to the mapping from variable to addresses in the memory, typically. When you evaluate a program, in fact, you map an address to a location in memory, and then at this location in memory, you have a value. And it's exactly this. So we now have a store and a stack, which is those two aspects. The stack maps variable to addresses, and the store now maps addresses to values. And because of this interaction, we will be able to keep the store unchanged and just change the stack by mapping variable to new addresses. It's getting much closer to what you can see in the implementation of the compiler. So now the big step semantics does not take statement and store, but it takes a statement, a stack, and a store because the couple stack plus store corresponds to the previous store we had. So it also produces a stack and a store. So here we are, and we can now write our semantics with these new ways of writing. So we also have a function bind. We replaced the store by the couple stack store because it's always necessary. And like before, we were producing a new store and an expression, and now we just produce a new store because we don't have to change the expression. Because we don't do the renaming anymore, so we're fine. So the signature of the big step semantics changed, and so it looks like this. So that's why we apply it here and here. And this is the evaluation of the body of the function, which was given by the bind function like in the previous approach. And now V is the evaluation directly of the return statement, because we don't need to change anything, because we use the store and the stack as an evaluation environment. What you can note here is that we don't need to change the value, the val function that was defined in the semantics course, because the val function was taking as parameter an expression and the store, but the store has a map from variable to values. And in fact, if you each time you need something like that, if you compose store and sigma, as it is here, you obtain a mapping from variable to values, and you just collapse the addresses that are in the middle. So you decompose when you need, and you just recompose when you want to evaluate something. Fine, and so now we can define our semantics by stating that if you want to evaluate a function call inside this new kind of store, stack plus store, then produce a stack plus store that is the store is changed as performed by the function, because this will change your memory. So this will have effect on your global variables typically and on the local ones, but there will be at addresses that you don't care about. And the trick here is that the stack, the mapping from variable to addresses, is modified inside the evaluation of the function itself, but you restore it here. So this is how you restore a variable. It looks a bit like it takes a few of inspiration from the first one, where you were taking back the store as it was before, but instead of modifying a store, you just forget the new allocations of variables you don't care about. So it's much more constructive than the first one, of course. Okay, so if you understood this principle, you will understand how the bind works. The bind, what it does is that it takes, as usual, but with a couple stack store here, and then it produces the body, which is unchanged. You don't have to rename anything, and a new stack. And the store that is the same as before, except that you put at new locations the evaluation of the parameters, and you will see how we do it. So the parameters are x1, the local variable are y1, ycar. This is like before, if you remember, but even if you don't, it's here. And I want fresh locations here. And what means fresh locations is that they are not yet in the store. And of course, you don't allocate twice the same fresh location. Okay, so this gives me the fresh locations. Then I want to give those values here. So I want to evaluate the parameters of the method call. So this is done by evaluating by the val function that we had before. We reuse the same tricks here to have something that looks like a previous store and gives me the value of the parameters. And now what I need is to update the stack. What is a stack? So the stack maps variables to addresses. So it's made from the previous stack, because I can always refer typically to global variables. And for each of the variables that are local to the function, that is both for the parameters and for the classical local variables, I create new locations that are here, and I map them to these locations inside Sigma. And now I have a fetch stack that maps everything to new things. And that's it. So one thing to be noticed is that you see now val e sigma is that we had before is replaced by val ei store composed with sigma. So it's everywhere in all the rules where you had this before, because you don't have the sigma doesn't have this good signature now anymore. So if you want me to recall the rule here, what this new rule does, what this new approach does, is that it replaces what was a store by a couple store and stack that adds the address in the middle. So I add this everywhere, which means here, there, and there, and there, and there, replaced by a couple. When I need to access a value, I do this kind of accesses to get back to what looked like the store before. And the ways can remain unchanged. The statements are unchanged because they are unchanged here. The store does not need strange manipulation. You just finally update the value of return here. I should come back on that, I should say. You should just update the store at the end by the return value, and the rest really looks similar. What you notice here is that, of course, the store update is a bit different because compared to what we had before, store update was done by x maps to v, and now it's done by sigma of x maps to v. Of course, the store maps addresses to values, and so I must get the address of x. I mean, that's kind of normal for the semantics. If you have the memory, and you want to update x here, you check inside this sigma here, not the one of the function, the one of the caller. Inside the sigma of the caller, what address is the good address for x, and now you map sigma of x to v. So that's the third solution that is a bit more complex, but quite closer to what exists in reality. So a few notes on the previous semantics. The stack is unstacked after each method invocation. You forget what was done here. You just keep the previous stack here. That's a way to restore the stack. Note number 2, when you build sigma prime, that is inside the bind function here, that is given here. It's quite big because it's sigma of before plus all the new variables. So of course I need all the new variables and I need the global variables. However, in sigma there's also the local variable of the caller, and I don't care about them. So I could forget them. But I mean, it's not mandatory. Just if it was too big, we could do it this way. It works with recursively defined blocks with local variables. So it's easier to deal with local variables in this way. The question is, do you see how? So I gave you a bit of time to think about it. I'll give the answer now. If you want to think more, just pause. You would deal with local variables by just popping a new sigma when entering the block. So it's easy to have an enter block rule that defines local variables and creates a new sigma that associates to the new variables. And when you get out of the block, which is easier to see in a big step semantics, because it will probably be evaluated inside one single rule, you would unpop those sigma in the same way as we did for function calls. With this approach, the memory grows in an unbounded way, but sigma is really bounded. So it's really bounded because it only maps the existing variable names, and you have a finite number of variable names. You could implement something like look like a garbage collector that removes the useless memory locations, or so it could be done by garbage collector that checks which locations are not referenced by sigma, or it could simply be done at the exit of the function because you know which addresses you've created, and so that's a place where you could just remove all the addresses you've created at the function call. So if you summarize a bit the advantages and drawbacks of the semantics, it's much closer to reality. The drawback is that we get a bit low level, so we have to deal with 2 levels for memory addressing, so we need a bit more small things to do. It modifies the whole semantics, but it's much closer to reality. And the good point is that statements are not modified upon call. We don't have renaming, and we don't have big store modifications. So the big change in the global semantics, so except that we need to pass a store and a stack to all statements, is the new assign rule that is exactly the same change as I did for the return statement. So that shouldn't change, it shouldn't surprise you. It's when I have an assign rule, I want to modify the store, but I cannot map x as I was doing before, because now I must find the address of x, and the address of x is sigma of x, which is given here. So that's a big change here in this rule. The rest is quite standard. The other rules are not much changed except that you pass around the stack and the store. As usual, I suggest, especially here, that we have a look at an example, and as usual, I suggest you to interrupt the video to try to do it by yourself, and then I'll give you one solution.
So at this point in time, you might be trying to unroll the semantics, and you might have wondered, hey, what is my initial state? So in the previous cases, we had an initial state that was the statement of the main and an empty store. But this doesn't work anymore because you want to have S, something of the form S sigma store. So you could say, oh, the store is empty, I don't initialize a variable as we had before. But you don't want, sigma cannot be empty. Because if it was empty, you wouldn't know where the variables are. If you have done it by yourself, you probably have found inspiration from the rule of call to function and applied something similar for the main. So in fact, if I suppose that dm are the variables for the main and d is a global variable, so this is main local declaration, this is global. You want to have the state statement S, but a sigma that is defined so that sigma is x I to l I, and let's call them ti to l prime I, where xi are the variables declared in D and ti are the variables declared in the local of the methods. You should have ti second because the local variables of the main might erase the global variables. This was noted if you have a look at the slides. You have a more formal way to write this is to say x1 xn is equals to the variables of D, and same for the other ones. So you want to have that, and you also want to have that the L I and the L and Li prime are fresh and disjoint. Probably fresh is not much of a problem because in your case there's nothing before, so fresh might not be very important here, but disjoint is, of course. If I come back to my example, and before unrolling the semantics, I could choose a initial sigma. I need x and y, so I could say sigma 0 map x to one fresh location, and now I need a notation for the locations that I didn't provide previously. I will just use integers and y for another fresh location, so that could be another one. I will use integers, but to not mess up with the other integers, I will just underline them in blue so that you can see what are the location. So now we can start. So if you have seen this video and you don't figure out before what to do with the initial state, perhaps you want now to try to unroll the semantics. So I have at hand the example and the rules as usual, and I will unroll them here in the video. So now that you know the initial state, things are a bit easier for the beginning. We have S, which is the statement for main. I have an initial sigma, which is a sigma 0 you've seen in the previous video, so I can write it in a corner. Remember, it's not the values, it's just the locations. And I should consider that I didn't initialize a variable for having a bit less things to do. So first statement is assignment. I will do it here because it changes a bit, because we've changed the rule for assignment. So in fact here we do the sequence, remember, and so we do the first element of the assignment, which is x becomes equals to 0 in sigma 0 empty. And this is just done once by the assignment rule, and it gives me so there's no statement anymore, it's just a resulting thing, which is the same sigma 0, the locations didn't change, but now we have x is mapped to 0, but remember now it's sigma of x, so it's at location 0 I map to 0. And then I have the remaining, which is, remember, y is 0 plus the main function call in sigma 0 and 0 to 0, and it will give me a couple that is the result. Okay, this is again a sequence, and for the left part it's very similar to before, so you will have whatever you have on the left, and in one big step you would obtain the same assignment, the same locations for variables, but now you have at the address 0 you have 0, and at the address 1 you have 0 too. So now I only have to do the function call, which is y. This is the other part of the sequence. F of 3 sigma 0, and this, I'll call this sigma. And this is where I'd apply the call rule, but the new call rule, of course, the third one. So now I have a look at what the call rule looks like. And as usual, I'll do it, I want the bottom, I'll do it upside, I want the premises upside down, so just because it's simpler to draw here. Bind 3 of F3. And now I have a new bind 3 call, and it returns me a statement S prime, which is, if you have a look carefully, it's the body of the function. So I can call it SF as is before. Remember, in my case, if you have a look at the example slide, it's, the body is X is assigned to 1 and Y is assigned to 2. I can write it here, it might be useful. So this is the SF, and the other part of the bind is sigma prime. And store, store, but I used sigma instead of store because it was taking less space, but and I'll call this sigma 1. And now I must know what is sigma prime and what is big sigma prime and sigma 1. Sigma prime, it is sigma, which was sigma 0, fine, but where with new locations for local variables, which is x in our case, which is mapped to something fresh, so neither 0 nor 1, so it will be 2. And there's also a local variable that is called y, what a surprise, and y is now mapped to the location 3. So basically you see that we've created 2 new locations. Okay, and sigma 1 is sigma, where I just assign parameters as usual, and if you look carefully, it's now L1 to V1, and where L1 is the location of the only parameter, which is x, so it's 2, now maps to the value of the parameter, which is 3. This is val of 3 in the right sigma 0. So it equals exactly to 0, 2, 0, 1, 2, 0, and 2, 2, 3. Fine, and then what do we need to do? So this was only the bind. I still have two the premises in my rule. First premise is SF sigma prime sigma 1, and this should reduce to something. It would be on the form sigma second sigma 2. In fact, here SF is just two assignments. The second of assign and assign. So I will skip this, it's just simple. You have sigma prime equals sigma second because it didn't change. So let me just take sigma prime here. It avoids one more equation. And then we can check the value of sigma 2. Sigma 2 just did the two assignments, so it's exactly 0, keeps at 0, 1, bind to 0. 2 is the location for x, so if you look at the statement, x is assigned to 1, so the value at location 2 is now 1, and y, which is at location 3 now maps to 2. The only thing I have to do is compute v, which is the value of x plus 1 in the combination of sigma 2 and sigma prime. And it's x plus 1, so I check x is at 2, 2 is 1, so 1 plus 1, it's 2. So now I can roll the end. If you look at the rule again, this keeps the same. This restores the sigma 0 I have here, and except that, so the store is sigma 2, whereby sigma of x in the rule, but here it's y, it's this variable here. So this is the location 1, and I bind it to 2 here. So it's sigma 0 of y, it's not sigma prime of y, because I get back to the context of the main. I can just up here denote that sigma 3 is sigma 2 where 1 is bound to 2. So it binds 0 to still 0, 1 to 2, 2 to 1, and 3 to 2. You can note that those two are inaccessible here, but still they are here. So here I have sigma 0, sigma 3, and I can finish the main rule with sigma 0, sigma 3. Here, so you can you can compare with the other semantics and realize that at least the values corresponding to the variables that are accessible are the same, and so we finish the main in the same accessible state at least.
If you remember from the semantics course, we defined several kinds of semantics, and in particular, we said that sometimes it's better to have a small step semantic than a big step semantics, depending on what you're trying to express and how you want to express things. You can have a look at the video to recall the differences, but to remind you rapidly, the difference between the two semantics is that big step tries to evaluate the whole program in a single big reduction, which involves sub-reductions, whether the small step semantics gives you how to do one step of evaluation. So it doesn't, you don't know how many steps you'll have to do to evaluate the whole program, and if you want to fully evaluate a program, you'll have to take the transitive closure, that is, apply the rules as much as you can until you reach something that is final. So this is what we will do here for functions. So first I want to recall here the base rules that we had for the normal minimal language without functions. So we had one rule for assignment that changing the value associated to x inside the store. So the signature of small step semantics is also a bit different because you have two possible signature. A small step rule always takes as on the left part statement and store, but it produces either a store or a statement plus a store. So the meaning is that if it first produces a store, that it means that it's a final result. And if it produces a statement plus a store, then it means that this is still to be evaluated to reach something. So the main rule that produces statement plus store is the rule for sequence. So for assignment, you simply modify the store by changing the value associated to x. Skip simply does nothing, it just returns the store as it is. For sequence is the most interesting part. If you want to evaluate a sequence S1, S2, you first evaluate the first statement, and two cases are possible. Either it returns it's a full evaluation, is the last step of reduction for S1, so this is a store. In that case, what remains to be evaluated is just S2 with this store, which can be evaluated in one or several steps. Or second possibility, S1 reduces to a couple S1 prime sigma prime. So this evaluation is not finished. For example, because S1 is in fact a sequence of two statements. And then in that case, you simply reduces S1 one step here. You just take that as a partial reduction, but you continue the evaluation still inside S1. We can have a look at the if rule. If you want to evaluate an if, you would first evaluate the condition, and if it's true, then that's it. You just remember that next step you will have to evaluate S1. The rule below is just the other case, the case where it's false. Okay, so first what I do here is that I take the old semantics, the previous one that you already knew, or that I already presented in a previous course, and I'll try to adapt it to the notion of stack store we had above. So this is just applying the same strategy as we had for the last big step semantics, but applied to small steps. So it's almost syntactical here. Instead of having simply a store, I have the couple sigma store as part of the configuration, the current state of the evaluation. So now the evaluation is a statement that has to be evaluated, a stack and a store, and something that I will put here in the middle, but for the moment, just consider it's not known yet. I'll fill the blank later. So it reduces same thing, either as a result, there's no question mark in the result. So if it's a result, it's just a couple sigma store with the store updated in case of an assignment. It's the same trick as we had before. To evaluate an expression, I must give something that associates variables to values, so it's a composition of store and sigma. And same thing, if I want to change the value of x, I must update the address. This is the address of x, in fact. The rest, skip is quite standard. You do nothing, and you just obtain sigma store. For the sequence, it's a direct adaptation from the previous one, where you just replaced the previous small sigma by a big sigma and store, which is exactly what the stack store couple. Same thing for the other. And same thing for the conditional. As usual, to evaluate something, I need to compose the store and the stack as written here, and that's it. The rest is just applying the same almost syntactical changes that as I had before. So now let's get to the question mark that I've put aside. The question mark will be the context of execution. It will replace the fact that when you watch Big Step Semantics, inside you have, in a single rule, you do a rule function call. So it's easy to know what was the stack before the invocation, because if you had a look before, the stack here is recovered here. So this on the left, it's before, and on the right, it's after the execution of the function. Here we cannot do that because we evaluate the function as a small step, so in plenty of steps, so we cannot remember from left to right. So we'll encode it inside the configuration. And in fact, the fact that we remember that corresponds exactly to the fact that in a real runtime, when you compile, you restack the context of the caller somewhere so that you can recover it later when you will get back from the function. So the question mark is now something much more, better defined, and it's a list of couple stack statement. So it's a list of what needs to be recovered when the function will be executed. So this operator here will be the list constructor. So context is a list of a stack statement. So now what you could consider is on the previous slide, the context didn't change. So you can, at each point where you have question mark, you can put ctx, which is the same variable. It doesn't change. It changes when you invoke a function. When you invoke a function, you first do as before. You first evaluate the bind function that gives you the statement, which is the content, which is the method body, and a new sigma and store. So this is the bind tree that we had before here. It's the same approach. We do the same thing. So it gives you the body sigma prime that is defined based on sigma, but giving new locations to freshly defined variables, and the store with new values for the locations of the parameters. Now suppose that I have a function call followed by something. Suppose it's a sequence with some statements. So now what you do is that you, in one step, you will do the function call. So this is before the function call, and this is at the first statement of the function. This is where the function starts. In one statement, you will start the function. You would modify sigma and store as given by the bind tree function, and you would change the context. You want to remember that when you will end the function, you will recover the statement as the stack sigma, and you want to remember where to put the return value from the function f. So I wrote it this way to basically I need to remember x and f here. So I've put it as this syntax because it looks like x is the is whatever is returned by f, but you could use another syntax if you prefer. The r of f is just a marker that remember the name of the function called. Is to be noticed is that x this the sequence x assigned to f semicolon s must be the whole current statement. It's the whole body of the function. I still have the rules that I defined above. If you have a look, it's just replacing the question mark by context. And now I need a new rule for the return. When the current computation finished, I must recover the previous computation. How do I recognize that the current computation finished? So if I'm still inside the function, it means that here I still have statement context sigma and store. At the moment where I end up with only this is a context with only a context sigma and store, it means that the evaluation of the function terminated. It's like when I was at the end of the execution of the program. And in that case, when I have only a context sigma underscore, then in one step, what I do is that I recover the previous evaluation context that I recovered, that I stored when doing the function call. So when I did the function call, I stored that, remember? So now I recover it, and I say, okay, as the function is terminated, I should start returning to the statement S, which is the continuation of the caller, what the caller was doing. So this is the continuation on the caller side, and this is the context that is afterwards, which is the next context, the next execution context, the next continuation is to be recovered after S is finished. And sigma is taken from here, so same thing from the context. And the store is almost unchanged, but I must update X with the value that is returned, and that's easy. I just assign to the location of X, the address of X, the value V that is given to me by this, which is the evaluation of the return statement of F, whatever is inside the return statement of F in the current couple store sigma. There are still two things that remain to be defined here. First is a small question. What do we have at the end of the execution when we finish evaluating? So when we have something now of this shape, we knew that we were finished of a function. We have finished a function, but sometimes it might be the main function. No, it is the main function if this is empty. So at the end of execution, I have something that looks like an empty context, sigma and store, and this is the sigma and store is the result of the evaluation. Forgive me, it's not. I don't have Greek letters here. And now that you have everything, I suggest that you try to evaluate, to apply this semantics on the evaluation of a program. The good point with operational semantics is that you can, if you only write the conclusion of your of the inferences, so it's enough to understand, to check that you've understood what was happening. Of course, if you were applying the rule properly, you must write the premises and check the premises. You can mostly focus on the conclusion and use the premises just when you need them. So I suggest you try.
So here is the illustrative example for the small step semantics. I already recall the sigma 0 and sigma prime that we had for the previous big step semantics. It will be the same here. The mechanism for allocating locations to variable is the same in the semantics than in the previous one. So I won't describe or re-obtain them again. It's exactly the same thing. Globally, I'll try to be a bit shorter in this explanation here because it's getting a bit long, I believe, for a video. So, as usual, I start from the main. I have sigma 0 and an empty store. It's a small step semantics, so we will do step by step, each time one statement. Most of the time, except for the function call and function return rule, I won't detail the premises, which are trivial. And here we have the intermediate step, so we can just advance. Here, the first statement here is x becomes 0. So you would believe me if I tell you that this gives me the remainder, so which is y is 0, y is f of 3 in still sigma 0, but now x 0 is mapped to 0. If you look carefully, this is done by the application of the sec rule and of the assign, the rule for sequence and the rule for assign. I'll let you do the details or ask me during the course. So we continue this way, and we do the assignment of y. It's similar, and we reach a state where we now have to deal with the function call in the same sigma 0, but where at location 0 we have 0, and like at location 1 we have 0 too. So if you look at the rule, it just unrolls the right bind function, which is the same as before, so I don't have much to do here. And I will end up with the new statement, which is the body of the function. I called that SF in the previous one, so it's assignment of x and y as usual. And I'm in sigma prime, exactly as before, and I had a sigma, which is this one. And which is no, not this one, of course, it's the one that maps 0 to 0, 1 to 0, and then 2 to 3 up. And here it's a context that we should recover, so it's in fact sigma 0, and y will become the return statement of the function f. I don't have continuation, so I omit the s here. So this is the continuation that will have to be recovered. Then we can skip a few steps and reach the end of the function, where we have at the end, we finished SF, so this is empty. We still have the continuation. Still sigma prime, and as we had in the previous example, 0 is 0, 1 is 0, 2 has been assigned to is x, so it has been assigned to 1, 3 to 2. Okay, and now I get the second interesting rule, which is the return rule, basically. And this unfolds this continuation here. And so I get the new sigma 0. In fact, I got a skip here if you want. I said that I omitted the skip, but it might not be that smart. Okay, and then I get the same sigma, so no, perhaps I can be a bit lazier and call this sigma 1, but updated with the return statement, and the return statement say sigma of x, which is the x here is this one, so it's 0, maps to v, and v equals whatever is in the return, so it's the evaluation of x plus 1 in the right store, which is sigma 1 composed with sigma prime. And this is 2, because x is 1 and 1 plus 1 is 2. And this will give me exactly the same sigma as we have had before.